Hello community! Today I'm gonna show you if we have PyTorch geometric, how we code heterogeneous graph learning. Now it is easy, we have the task of a node classification, and compared to last time where I showed you it is in a homogeneous graph, this time we have multiple node types. So last time we only had persons and a link and persons and a link. Now we have multiple node types. This is it. So first, of course, we have to again import all our dependencies. If you have not seen my last video, we are working here with an instance of torch geometric data.data. This is the object that holds our attributes for our graph. You have to know about three features, data.x. This is what we called the node feature matrix, with the shape, the number of nodes and the number of node features in our node feature tensor. The second is the edge index. This is the connectivity and it has the shape 2. This is default. And the number of edges. You can deduct the number of edges from this particular parameter and the edge attribute. This is, of course, the edge feature matrix, very similar to the node feature matrix for node. Now for each edge, we can have features. And it has a particular shape in PyTorch. This is the number of edges and the number of edge features. I showed you all of this in my last video. I leave you the link to the last video. We just need to install the dependencies. So we have a pip install the sentence transformer, our SBERT. Then we have, of course, import torch, and we import here, as you can see, PyTorch geometric from the Git. Beautiful. You have here, if you do it like I, the CUDA version 1.1.3. And then you just import some dependencies regarding torch geometric, the dataset we're going to use, and then the hetero data for the heterogeneous graph, of course. And then we do some split and some to undirect. When we want to split our dataset into test dataset, into training dataset, and then the evaluation dataset. You're familiar with this from your ML models. Of course, we need some pandas. We need our sentence transformers, of course, our SBERT, and we will have a little bit of graphics. So we need matplotlib and Seaborn. This is it. We activate this, we run it, and we are ready to go to our heterogeneous graph learning with PyTorch geometric. So let's start. At first, we need a dataset, and we have here a movie lens dataset. This is a heterogeneous dataset. We just load it, but what you have to know, it consists now of nodes of two different types. In the last homogeneous dataset, we just had the type person as the type of a node. Now we have two types of nodes. We have a node with the type movie, so thousands of movies, and we have a node of the type users. Thousands of users rate the movie. Beautiful. User ratings for movies are available as ground truth labels for the edges between the users and the movie. So we just downloaded it. If you want to know a little bit about it, it contains about 100,000 ratings. And the set is about, the smallest set that I download here is about close to 10,000 movies. It was evaluated by 610 users. So keep in mind, 100,000 ratings, about 10,000 movies, and about 610 users. Here we go. Beautiful. So at first we have to import it. I want to show you here. I already have it here. I have created a directory, movie lens. And there I have my CSV file I downloaded from the internet, the movie CSV and the rating CSV. So how do we now transform this and bring it in a data pipeline that we can use in PyTorch geometric? Easy. At first we say the movie path goes to our movie CSV file and the rating path goes to our rating CSV file. Beautiful. Now get an idea, we have a look at the panda. But we can do much nicer. I prepared already something for you here. Beautiful. Just give me an idea. I just clear the outputs. Otherwise, you will be a little bit. Yes, here. I want to see this here. So, sorry. Here's what we have. We have a movie ID. The movie title, Toy Story, has the numerical code 1. And then we have the genre to this particular movie. And we have multiple genre, heterogeneous graph. We have adventure, animation, children, comedy, fantasy. And then this movie is evaluated, rated by different people, 610 people. So the first user gets the number 1, and his rating in a scale from 1 to 5 is 4. Beautiful. And then we have thousands of data sets. Beautiful. The first, as always, we check that data are not missing. So is null, is beautiful. We have all the data. And then we just have a look at this. We do a group by. So you see, and we do sorting of value. You see here the different movies and the different ratings. You can do whatever sorting you like. But what I'm gonna look at is, for example, here, I look at the rating. So you see here from 0 to 5, or from 1 to 5, no, 0 to 5. And then the number of ratings for each particular scale. And you see here, always good to know where's your maximum. You have here about 4. You have the maximum number of votes, more than 300 votes. They gave a 4 or 4.1, 4.2, whatever. This is just to get familiar with the data set. So now here we go. Now I have a lot of text. Sorry, I just write it down that you can read it. You don't have to listen to me. If you ignore this text and you just listen, you are fine, no problem. So for representing this data in our Panda data frame, we have to transform it now, of course, in a PyTorch geometric data format. So to do so, we define a load function. So we load now the node CSV file, and we do it in a very easy way. So it reads at first the CSV file. Well, unbelievable. We would not believe this. And then it returns a node level feature representation with a particular shape. And this is the shape that we need, the number of nodes and the number of features. Beautiful. So we read the file. We have a mapping that is more or less one-on-one. And then we have an encoder. And the encoder is the interesting thing, if you want, because it tells us exactly, yes, I'll give you a second. Load reads the CSV file, creates a dictionary mapping that maps its index column to, so again, it maps its index column of the file to a consecutive value in the range from 0 to number of rows minus 1. This is needed as we want our final data representation to be as compact as possible. This means the representation of a movie in the first row should be accessible via our feature tensor. Beautiful. So this is the function we define, and it returns to us exactly what we are looking for. We are looking for our x. And if you remember, well, hold on a sec. X, if you're new to this, X is our node feature, here we go, .x, our node feature matrix with the shape, the number of nodes, and the number of node features. Beautiful. So here we go. Where are we? So beautiful. An interrupt. Just to help you understand. Feature extraction. What is this feature tensor? So we use now an example to understand feature extraction with a vectorizer. So to have here easiest example you can imagine, we have 2 sentences. This is a good job. I will not miss it for anything different than quantum. Doesn't make any sense. Never mind. Sentence 2. This is not good at all for quantum equivalation. You see, we have common words, quantum and quantum. What about Christmas evening? So we have more or less 4 sentences, but never mind, because this is all the text that we are now encoding. And we define this is the sentence, or the string length 1 and the string 2. Now, you are familiar with vectorization. We have this as a fixed function in scikit-learn in the feature extraction. So we say, yes, beautiful, do this to me and show me the result. So here we go. Oh, sorry. At first we do, of course, n-gram 1 to 1. And now we have here, we eliminate the stop words in English, and we have sentence 1 and sentence 2, and we feed it into our vectorization. Now, you see here, sentence 1, where sentence 1, this here, suddenly becomes here, sentence 1, the vector representation. How we do this? We take each word that is within both sentences, and we say here, okay, is it in? Yeah, and then give us a kind of an animation. This is all done for you in the vectorizer. So you can see here, Christmas is, for example, not in the first sentence, but it is in the second sentence. Let's plot this. Christmas is in the second sentence, but not in the first sentence. Great. So suddenly we achieved a vectorization of a text, of a string of characters. Beautiful. Now the nice thing is we don't have to stick some to a vectorizer, to a classical vectorizer where you just do some counting and some normalization. But hey, we know about sentence transformers, and here comes the nice part. We have now sentence transformer vector embedding of our movie titles. Remember our movie titles? Where are they? Where are they? Here. Movie title: Forrest Gump, Pulp Fiction, Silence of the Lambs, Star Wars. These are all text. So beautiful. We know SBERT. We have hundreds of videos on SBERT on my channel. So we now do exactly this. Instead of just a normal vectorization, we make it in a clever way. We use a sentence transformer. You're familiar with this notation here in Python because I showed you several times a specific model we use. This is already a pre-trained model that is available on Hugging Face for you. This has been trained on millions of documents in the English language, so it is absolutely up and ready to go. And we use this model that is available ready for us. Beautiful. And what we do is, well, very easy. The sequence encoders, what we call this class here, encodes our raw column string. This is the movie name into an vector embedding. Beautiful. This is exactly how you use SBERT. So we define this function, convert the movie names into a vector. You see here, this is a normal vectorization. The movie words, now we have sentences, and we apply now the BERT model on the sentences. So a little bit more advanced. And we get a very nice vector representation of the first sentence that is, of course, completely different to this vector representation. But hey, if we have intelligent system, why not use intelligent system? So, beautiful. SBERT define a sequence encoder that encode the row. Yes, 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 yes. We can use the sequence encoder to encode the title of the movie file. I just told you about this, everything. Now there's another information that we have. Remember I showed you that here we have the movie title. This is a string, this is text. But hey, here's also text that we can use and we can vectorize for the input in our PyTorch geometric model. So we built now a data pipeline where also our genres, we use now this for a vectorization. So we are now at the genre, just that you know where we are. I lost everything, and here we are. In a similar fashion to our movie titles, we can create now another encoder. This is our encoder. Where is our encoder? I don't see the encoder. Genre encoder splits the row column strings by separator and converts our individual elements to categorical labels. So what it does, as you can see here, I told you we have here a word, then we have a separator, another word, and then we have a separator. And the task is now, well, we convert this to a categorical level. We analyze the old data set and we say adventure becomes, I don't know, category 1. Animation becomes category 2 and so on. So what we do is easy. Let's do this. This is a function. Where am I? This is SBERT. Genre encoder. Here we are. And converts these single words we have now into genre representation to categorical labels. Beautiful. With this, we can obtain our final representation now of the movie data. And now it comes. Now we put everything together. Now we have this function that loads now our node.csv file. And we have two encoders. We have an encoder where we encode the title string, the title sequence, in characters, we have now a sequence encoder that gives us a vector representation of the movie title. And the movie genre, we built a genre encoder that gives us also a categorical label. So, genre encoder, yes, categorical label, beautiful. So let's, have I executed this? Yes, do it again, then. So let's do this. This takes, of course, some time because now we have to download this sequence, the SBERT model for the sequence encoder from Hugging Face. We have to apply it, and I only use here, I think I'm on a CPU only. I have no hardware acceleration. We don't want to take away this GPU resource from anybody who is doing research. This is just to show you how it works. So I will be back with you in about 2 minutes and 20 seconds. And here we are again. So what have we achieved with this? Now we have for each node type, whereas there's a movie node type, we have now encoded this textual information of the movie title and the genre into a vector representation. And at first we have to look at how sentence transformer, how SBERT performed when we encoded the movie title. Now this is easy to see. How do we look now? We have now our feature tensor of the node type movie. And here we go. Now, of course, you say, okay, what's the shape? Is this the real shape? Yes, we have 9,742 different movie titles, and we have an encoding now in the number of features in a 404-dimensional way. So if you want to look at the first one, the first movie title here, this is now here the exact array with 404 dimensional representations. So, okay, great. The second is the movie mapping. I told you the movie mapping is the genre of movies now in a categorical label encoding. This is very easy. This is almost nothing. It is, of course, a dictionary. We have all the 9,742 movies. And the movie mapping just shows you how you map this here. It's a dictionary. Great. Doesn't help us at all. And yes, this is now for the movie titles. So the second is we now use the same functionality now here, our load node CSV function. Remember our node CSV function, where are we? Where are we? Our load node CSV function. And we applied this with a specific path to a specific CSV file. Now we have, you remember, we have two CSV files. We have movies and ratings. And up until now, we only applied it to movies. Hey, but we have a second file. What a coincidence. Yeah. So we go back and we say, now we apply the same functionality that I just showed you now to the second CSV file. I don't have to go through all of this. You know what's happening. Let's just do it. Now the beautiful is that suddenly we have now a user mapping. But a user mapping is very easy. We do not have a specific additional information to the users. What is their age, or are they male, female, or are they living in US or Europe or in India? We have no information about this. So user mapping is really easy. It is more or less a one-to-one mapping. We have no additional information. We have no encoder on this because we have no information. So you see, this is an easy task. Beautiful. And now comes the part where we put it all together. Now we are with the heterogeneous graph learning part where we have to put this into a PyTorch geometric specific representation. So first we create a data object of the type torch geometric data heterogeneous data. Hello, we have a new command for which we define the node feature tensors, the edge index tensors, and the edge feature tensors individually, and this is the most important point, for each type. Beautiful. You remember? Just let's go back. Yes, yes, yes. We have the node feature matrix. We have the edge feature matrix, and we have the edge index. This gives us the graph connectivity, and it shows us the number of edges. So whatever we have here, now we have to define this for the heterogeneous graph learning case. Beautiful. Yes, 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 I told you this. Anything else due today? Yeah, a set of types need to be specified for node and edges, each having its own data tensor. So imagine to each node, we now attach a tensor, we assign a tensor. If you have node type 1, we attach a tensor with the information we have about this node type. If you have a node type 2, we attach a data tensor. If you have an edge, we attach a tensor to the edge. So the graph is filled with tensors attached to every object in our graph. Beautiful. Now, as a consequence now of the different, more complex data structure, the message passing formulation changes. Before we had a homogeneous graph, and now we have a lot of graphs and a lot of edges from different types of nodes. So we have now also to change the message passing formulation, allowing for the computation of messages and update functions, conditions on node or edge type. Great. So let's start here. Yeah, the user mapping I showed you, this is just more or less a one-to-one encoding that we have no information about the users. Just to show you, because we are gonna start now here. So we already imported it, but again, our heterogeneous data, our torch geometric data.heterogeneous data. And then we say, okay, the data we're gonna create now are heterogeneous data sets. Beautiful. And we define it. So we have here with the data, we define now a node type user with the number of node is simply the length of our user mapping. This should be 610. Clear the output. And the data now for movies, we just created movie underscore x. Do you remember movie underscore x, what it is? Let me show you. Movie underscore x is our sentence transformer, our SBERT encoded vector representation, our embedding of the movie titles. So this is our beautiful movie x tensor, and you can see, yes, full tensor fledged. Here's our tensor. So we're gonna take this now, and we say, hey, in our heterogeneous dataset, now for the node type movie, this is the information. Please attach to our 9700 nodes this particular tensor, each particular tensor. So let's have a look at this. Beautiful. Here we are. We have now a heterogeneous data, and we have two node types. The first node type is user. It tells us the number of the nodes is 610 because we have 610 people who classified, who evaluated if they like the movie or not. And then, of course, we have the node type movie in our graph. And for this, we have a particular feature tensor, and it tells us, you remember the feature tensor tells us, we go back, the feature tensor tells us, the node feature matrix tells us the number of nodes and the number of node features. Right. Oops, no, here. Yeah. So the number of nodes, 9742, and the dimensionality of the features, 404, because this is what we get out of our SBERT model. This is the dimensionality of the tensor. Okay, so you say, hey, great, so we have our heterogeneous data set, but we only have nodes. Where are the edges? Well, to your surprise, we will do now exactly the same to the edges. And as you can see, we used here the feature tensor representation of our nodes for the node type movie. And you know, we already have an edge feature representation, and we're going to build now the edge feature tensor and edge feature representation. Beautiful. So next to the edges in our graph, we have the edge feature tensor. Beautiful. So what we do? Remember we had a function where we said load node CSV. Now we do the same, absolutely the same for load edge CSV. We have again the path, and we have here the different indexes of the file, the name of the columns in our CSV file. It is beautiful. I have written here some explanation. Oops, sorry. If you want to read it, it's all there for you, but it is really similar to our load node CSV function. We have now the load edge function from a different file. So now to our encoder. What can we encode on information? And this is the important part. Encoders are used to return additional, now edge level, feature information. So for example, the loading of the ratings from the rating columns in our CSV file with the ratings. Beautiful. Now our ratings are easy because it is, I don't know, 2.1 or 4.2. So we can define now an identity encoder that simply converts this list of floating point values, 2.4, into a PyTorch tensor. And of course, we need as an input not a classical normal value, but we have to convert everything to a PyTorch tensor. And this is what our identity encoder does. The identity encoder takes the raw column values, 2.4, and converts them into a PyTorch tensor. And you are not going to believe that has the value 2.4. Beautiful. Oh, yeah, we have to do this. Have I done this? I don't know. Just let's run it that we have it. So, and now we're ready to finalize our heterogeneous data object in PyG. So here we go. We do the same as before with the node CSV. We now load the edge CSV file. And of course, there's the rating path to our ratings CSV file. And then we take the user ID who rated a movie with an ID. And we have the encoder. Our encoder is just a numerical value, the rating value itself. And this, I just showed you, we use an identity encoder that converts an integer to our PyTorch tensor. So this is all the complexity that we have to take care of, but we have to take care of it. Having done this, what we get out of this is an edge index and an edge label for this particular part. So what we do, we define now our data. You remember data is our heterogeneous data set. We define now the edges. We already have the nodes, now to the edges. The edge is, of course, a triplet. It starts from the first node, from the source node, if you want, the user node type, and it goes to the movie node type, the destination node type. We have two node types. And in between, we have our edge. And our edge has the feature, or if you want, just call it rates. So the user rates a movie. Beautiful. And for this, we have an edge index, we just calculated here. And for this exactly same, we have an edge label. Beautiful. Edge label is also calculated here. And now we can put it all together. And if we now have a look at our heterogeneous dataset in PyG, what we achieved. We have our two node types declarations with our specific data. You remember, the user is just the number of the user because we have no demographic data about the user. But in the movie, you know, in the movie we have the title and we have also information about the genre. So here we go. This is our movie with the specific encoder we had for our movie titles, where we had the SBERT vector encoding. And now the new part is here, and this is here. There's a bracket missing somewhere. Okay. There's a bracket missing. Very interesting. And then here in blue, we have now our edges, our edge information encoded. So we have an edge from the node type user to the node type movie, and our edge is functionality rates. And we calculated now, as I showed you here, our edge index and our edge label. So we have now our edge index, we have 100,000 edges, and the edge label, we have also 100,000 labels with type 1. Beautiful. This is now our heterogeneous data set that we can use now for training in PyG our ML models. And you can use a very normal GNN model. But at first, of course, we have to do some transformation. And there is also a library, so you just say, hey, beautiful, this is a transformer. And we have some random link split and some two undirected. I'll show you in a second what we do with this. Now we can convert our data into an appropriate format for training a graph-based machine learning model. Beautiful. This is the official coding. So at first, we have to add a reverse relation for message passing because it has to go forward and backward. Beautiful. How we do this? Well, we have an edge definition that tells us, hey, we go from the movie now, so from the destination. We have a reverse rates. We go to the user. So this is exactly the time reversal of our normal edge relation. And we have a function already defined for us, to undirected. So we say data is equals to undirected of the data. And so what it does, to undirected transforms a directed graph into a PyG representation of an undirected graph by adding reverse edges for all edges in the graph. Beautiful. Therefore, future message passing is performed in both directions on all edges. This is what we wanted to achieve. Beautiful. Yes, you can have some self loops and you can normalize everything, but second point is, after you have done this, you have now, as you know, in every ML model, you have to split your dataset into the training dataset, the validation dataset, and the test dataset. And this is exactly what we do. Here we go. I have to execute this. And now you see we have, with this transform command, we have now a training dataset, a validation dataset in PyG, and a test dataset that is absolutely compatible with PyG. So let's have a look at this. Now the first set is, of course, our big training data set. Here we go. This is our training data set. A heterogeneous training data set. As you can see, we have again two node types: user 610 no encoder and movie with an encoded. And then we have here our edges. And you see here we have now the edge, let's say, in direction 1, and this is more or less the reverse edge. You go from user rates movie, you go to movie reverse rates user. So bidirectional. Beautiful. And the information, of course, here is our edge index, our edge label, and the edge label index. So we have, from our 100,000 edges, we have now in the training data set, we have about 85,700 edges in our training data set. Now, the next is the validation data set. In the validation data set, this is here. We have the same, the number of nodes, the number of movies identical, but now we have only a label index. You see here 5,000 edges here in our heterogeneous data. And if you go now to the, I think it's the evaluation, the test data set, yeah, this is here, right, our test data set. So, and you see here, we are now here at 10,083 edges that we reserve for the testing. And in total, remember, we had 100,000, so here we have 85,000, 5,000, and 10,000. Beautiful. We split up our data set and we are ready to go. Now we created an intelligent data pipeline for our heterogeneous PyG graph neural network model. My goodness. Up until now, we just prepared the data. And this is so important. The main part is data. A lot of people think that it is only to write the ML model. No. If you are not good in preparing your data pipeline, it all depends on the data. Please do not forget, data are so important. So now comes the second huge chunk. How do we code a heterogeneous PyG-GNN model? Now, with PyG, I think it was 2.0, you have now the possibility to train heterogeneous GNNs. So you remember, standard message passing GNN or MP-GNN cannot trivially be applied to heterogeneous graph data, as node and edge features from different node types and edge types cannot be processed by the same functions to different feature types, maybe different dimensions, different notation, different format, whatever. Now, what is the solution? Here is the solution. A natural way to circumvent this is to implement message and update functions individually for each edge type. You say, heaven's sake. So we have now a graph and we split this graph in, I don't know, 2, 3, 4, 5. It's not a subgraph. Yeah, it is a subgraph mathematically, but for each edge type, we define an own functionality for message passing, update function, and so aggregation and whatever. So during runtime, yes, iterate, yes. So to avoid unnecessary runtime overheads, PyG has done this for us, and we have 3 ways. Now, the first one is the easy one. I'll show you the first one. You can automatically, and I want to emphasize automatically, convert a homogeneous GNN model to a heterogeneous GNN model by making use of a certain command. And this is PyTorch geometric to hetero. Beautiful, or hetero with base. Of course, you can write your own heterogeneous GNN operators. So, and just to show you if you would do this, I take here an example. I have here the link for you. There's a beautiful documentation on PyTorch geometric. Read the docs.io. You find everything over there. So as you can see here, we have here our GNN model. This is the model I showed you already 3 times. Now we just have, instead of a linear layer or a GCN, a graph convolutional layer, we have now Sage convolution with 2 layers. At first, of course, you have input and hidden layers, and then you have the output layers. And I'll show you the -1 notation in a second. And we have simply a feed-forward network that shows us layer 1 with a ReLU functionality and then the layer 2. This is it. And how you do it, in theory, is this is the model you define. You remember the GNN model we just defined here. We have the hidden channels is 64. And then here we come to the command you have been waiting for. You say model equals to heterogeneous. You put in the model, you put in the metadata, and you do in the aggregation function. This is, of course, a summation. And this is it. PyTorch geometric will do for you heterogeneous graph learning with this command to hetero model and aggregation function. This process takes an existing GNN model and duplicates the message function to work on each specific type individually. So this is the way to do heterogeneous graph learning on PyGraph. PyG, my goodness. And let's switch over to exactly this link that I can show you. If you want to know a little bit about it, here's the official documentation. You have here another example, heterogeneous graph learning. Have a look at the graph, but what I want to show you was just the -1. So where are we? Heterogeneous graph, heterogeneous graph transformation. I already showed you how to do the t-indirect. Creating, automating, yes, this is here exactly what I showed you. Now to this -1 notation. Whenever you find something, have a look at the original literature. So you see here they tell you if you switch from the homogeneous model to the heterogeneous model, process takes an existing GNN model and duplicates the message function to work on each edge type individually. Beautiful. System does this for you. Beautiful. Now, and here the note where this -1 comes in. Since the number of input features and thus the size of the tensors varies between the different types, PyG can make use of lazy initialization to initialize the parameters in a heterogeneous graph neural network as denoted by -1 in the in-channel argument. This is exactly here, such convolution. We have now the in-channel argument and we have -1, -1. Please keep in note, there's this beautiful notation. Use it. This allows us to avoid calculating and keeping track of all tensor sizes by the computation graph. Lazy initialization is supported for all existing PyG operators. Beautiful. If you want to learn more about it, there's a lot of training examples for you to have a deep dive. I recommend definitely that you go directly here to PyTorch Geometric, read the docs AI, and as you can see, we are here in Heterogeneous Graph Learning. I took all my examples from here, and if you want to have here more examples for you to learn, there are also some beautiful documentation. This is the very first graph we had a look in, and here you find all the data you need. If you want to continue learning, I recommend here the Stanford CS224 Winter Graph machine learning tutorials. They have here a specific PyTorch geometric tutorial project, and you have here the COLAB notebooks and videos on those specific topics. So if you want to have a deep dive in spectral graph convolution layers, or if you want to go in graph autoencoders, you have an executable Jupyter notebook and a video explanation for this. If you want to have Node2Vec, I have a specific video on Node2Vec that I programmed in TensorFlow, but of course you can have here a notebook and you do this computation in PyG. Data handling, graph pooling, notebooks, this is the literature I recommend to you if you want to get familiar with PyG. I say this is it for me. I just wanted to show you here the data handling, the intelligent PyG data pipelines we need if we want to convert our CSV data. And I show you here loading graphs from CSV. This is it. If we want to load the graph information for PyG from classical CSV file, you have to prepare all your data. You have to look at this in detail. And this is the way you can create heterogeneous graph data sets for node classification task with PyG, PyTorch Geometric. I say thank you, and I hope I see you in my next video.